Good morning. I will continue the discussion on grain size analysis. We're supposed to have an online class today, but there is a little change in the schedule. So I want you to just view this video as part of our lecture. So to determine the grain size analysis, we normally use mechanical analysis. This is the method to evaluate the grain size or the particle size distribution of soil. So if we have a soil mass, how do we know how much percentage has this particular grain size, or how do we distribute the particle size in a particular soil mass? Now, there are two methods to use to analyze the soil, and the first one is the sieve analysis, and the other one is the hydrometer analysis. Now, sieve analysis is used for particle size larger than 0.075 millimeter in diameter. So if you remember the USCS method, or the Unified Soil Classification System method that was previously discussed, or we had an overview of the USCS method, the soil that has particle size smaller than 0.075 is considered silt or clay materials, or it is termed as fines. So meaning to say, the sieve analysis can only evaluate soil larger than 0.075, or soils that are not considered silt or clay, or soils that are not considered fine materials. And the hydrometer analysis is the one used to evaluate these very small particles. So for those particle size is smaller than 0.075 millimeter in diameter, then we use hydrometer analysis instead of sieve analysis. And the figure here on the right shows a sample of grain size distribution curve. This is a relation between the particle diameter. The graph shows the relation of the particle diameter versus the percentage finer, or percentage passing. So sometimes you see the word percentage finer, or sometimes it is percentage passing. Okay, there are two uh, division here. This part shows result of a sieve analysis, and this part shows results of hydrometer analysis. So meaning to say, you can combine the results of these two analysis method. And these data points here are the point where you see the percent finer of a soil versus the particle diameter. And you see a point or a part here in the curve that some points are somewhat away from the curve. And this part, these triangular data points, are ready for hydrometer analysis. Later you would understand why, but just to give you an idea, because of the assumptions in the hydrometer analysis, so there are some points in the initial reading that may cause this deviation to the curve. But it's okay because you can still get the regression curve, or you can connect the points rather, not the regression curve, for all the data points and develop the grain size distribution curve. So this is a sieve set that is used for the sieve analysis. So we call this sieve set. These are being piled up, and there's a pan at the bottom. So this one has, like, it has an opening. Every sieve has an opening with different sizes. like this one. Let me show you. Okay, so every sieve set, the top view is like this, and the, the opening gets smaller and smaller. And it has sieve number depending on their opening, just like that. So like this one, it can be, the opening is 4.75 millimeter, and like this one is 0.075 millimeter. So see the difference. This one is very, very small. Yeah, the 4.75. So it has like number. This is number 4 sieve set, and this is number 200 sieve. And in between, there is number 10, number 20, 80, number 100, and it has corresponding diameter or opening, size of opening. So why did I put as an example the number 4? Because as the procedure, let me show you the procedure. The sieve are piled up with a pan at the bottom. So there's a pan here at the bottom that of course will catch all the soil after it passes through the series of sieve set. The soil sample is placed into the sieve at the top. Okay, so the largest opening is placed on the top, and the smallest sieve opening is placed before the pan. And then this is being shaken, this is covered and being shaken for a required amount of time in the sieve shaker. Normally we have a sieve shaker. At the end, soil samples, after, after shaking it, the soil samples retained in each sieve and the pan are weighed. The sieve analysis may be carried out with soil samples in either dry or wet condition. So let's say this one is number 4, or the one I showed you earlier that has a 4.75 millimeter opening, and then this are series of sieve sets where the diameter decreases or the opening decreases, and then at the bottom is the pan. So all we have to do is to put the soil sample here on top, and then shake it up, or put that in a sieve shaker, and then when it's been shaken, of course the soil sample that is smaller than the opening will go down and go down and go down and go down here. And then after, okay, let me show you again. Right, this one is 4.75, just to give you an idea. The 4.75, the soil that is retained on this sieve is considered, retained on number 4 is considered gravel. Okay? And the one that passes number 4 are considered sand up to retaining number 200. Okay? So this is still considered sand. But the one that passes the number 200 is considered fines or silt and clay materials. So from there, you can determine how much percentage is the gravel, the sand, and the fine particles. That is being done in the laboratory actually, but we'll have an example on that. Okay, now for the hydrometer analysis, since the particle size 0.075 is so small, instead of using a sieve set, a hydrometer set is being used to measure the particle size finer than 0.075 millimeter because it's very, very small already. Now, hydrometer analysis consists of course, hydrometer, this one. This is a hydrometer. It has like a lead at the bottom of this small bulb. And then you have a like a thermometer here that measures the density of our soil. And then we have here a graduated cylinder. Then we have here our soil mixture. Okay, the principle of hydrometer analysis is based on Stokes' law. So try to imagine that we are only considering the particles, the very, very small particle size, and that this particle size is assumed to be spheres. Spheres, so, but not in reality, not all particle size are spheres, right? But the assumption is they are spheres. And based on Stokes' law, the soil, when mixed with water, of course, at a certain point, it will be sedimented at the bottom. So Stokes' law is a principle of sedimentation of soil grains in water. Of course, when you mix it with water and the soil particles have different particle size, at a certain point in time, the soil particles will go down and get sedimented at the bottom. And of course, the larger particle size will go down first than the smaller particle size. So the principle is the terminal velocity of soil particles is proportional to the grain size. So if the particle size is large, the velocity is faster or higher than the smaller particle size. So it is proportional to the grain size. Then, while the particle size are going down to the bottom of the cylinder, the density of the soil and water mixture will be measured using this hydrometer apparatus. And it will be done at different time of sedimentation. So the process or the principle of hydrometer will help us to indirectly determine the grain size of the particles larger than 0.075, or so you can actually get the percentage of the particle size for soil less than 0.075. Okay, so that's the principle of hydrometer analysis. So it is the same. The principle will, or the method will also determine the percentage finer and the diameter size. If you go back to this graph, you can plot the particle diameter versus the percentage finer or the percentage passing. Okay, so that's the two methods that can be used to determine the grain size or the particle size of the soil. So what are the applications of having this grain size data from the grain size distribution curve, or what we call GSD, grain size distribution curve, we can actually get three very important parameters, which are the effective size, or D sub 10, the uniformity coefficient, or C sub U, and the coefficient of gradation, or C sub C. So these three parameters, soil parameters, are obtained from this graph and be calculated, or can be calculated based on the data from this graph for the purpose of classifying the soil later in our succeeding topics. So just to give you an idea, the effective size is derived by, some of the very famous researchers, and says that when you use the D sub 10, this is providing, very good results. That's why it's called effective size or effective diameter. All right, so how do we get these values? So from the grain size distribution curve, again, this shows the relation of the grain size, or the particle size, or the particle diameter versus the percent finer. You simply get, for the effective size, let's say for the effective size, you simply get the diameter at 10% finer. So from this plot, if this is your grain size, you just get the 10%, or this is your percent finer rather, the 10% finer is this one. You just extend it to your curve, and the intersection, when you extend that, from the intersection, you extend it downward, and whatever the grain size at that point, that is your D sub 10. While for the C sub C, you can use the formula D sub 30 square over D sub 60 times D sub 10. And for C sub U, we have D sub 60 divided by D sub 10. So again, this values below, or the subscript, is the percentage finer, and D is the unknown, which is the diameter. So from the grain size, you just go to the percent finer, let's say percent finer 30%, extend that towards your curve, and then from the intersection, you extend it again downward to get your D sub 30. Similarly, for the 60% finer, you get a horizontal line towards your GSD curve, and then from their intersection, you extend it downward, and whatever the diameter at that point, that is what you call your D sub 60. So this is a diameter value so that you can get your C sub C and C sub U. Again, the purpose of those is for classifying the soil later on. Other uses of grain size data is to describe the characteristics of the grain size distribution of a soil sample. For example, the soil can be poorly graded or well-graded soil. A poorly graded soil are soils that most of the soil grains are having the same size. So here is a sample of poorly graded. So no other particle size except for like same sizes. And that can be evaluated from the grain size data. While well-graded soil shows that the particle sizes are distributed over a wide range. So like this one, this is a well-graded soil. And for the gap-graded soil, a soil might have a combination of two or more uniformly graded fractions. So you only have like one or two sizes in your soil sample. Okay, so this is very important to understand for you to know that if your soil sample has just the same sizes or a mixture of different particle sizes, because like for this one, for the poorly graded, the voids are more than the well-graded sample, because if you have smaller particles, it can fill in the spaces in between the larger particles, and so it could be more dense or it could be less voids, unlike the poorly graded one. Okay, so I think that ends for the mechanical analysis of soil, and these are the references for this particular discussion. Thank you.